Hello everyone, welcome to another pre-recorded lesson for AP Chemistry. Today we are going to be going over the material covered in Topic 2 of Unit 1, dealing with things like mass spectrums. One of the unit objectives is to be able to explain the relationship between what is called a mass spectrum and the isotopes of an element. This topic in particular, we're going to be able to determine the identity of an element based on the number of isotopes, as well as its abundance. Then finally, be able to calculate the average atomic mass of an element, given that it is a weighted average of all of its isotopic masses. So a quick little review, okay, and this was a question that showed up in a previous quiz, and that is the definition of an isotope, okay? An atom of an element with a different number of what? Neutrons, okay? Because you remember in my class we learned the 3 I's. Protons determine the identity, electrons determine the ions, and neutrons determine the isotopes. Okay, so here's a picture of uranium. Now, there are 2 ways of communicating isotopes. The most common way is simply the element symbol followed by the atomic mass. And again, quick little review. What subatomic particles are considered to determine the atomic mass? And that is protons and neutrons. Electrons, their mass is negligible. Okay, so a little sidetrack, but this is the most common way we write isotopes. Another one is the atomic symbols, where we have the element symbol. On the upper left, we have the atomic mass. What is not shown really on the bottom left is what piece of information? The atomic number. Okay. All right, so mass spectroscopy is a very common, very popular technique, all right, that measures the mass to charge ratio of ions. Okay, and initially it's a very good technique to identify or confirm the presence of a compound or an element. Okay, here is a very, very rudimentary diagram of mass spectroscopy. Now, you do not need to know any of this information, but it's insightful to know how a mass spectrometer works. Okay, and I'll try and keep this brief. But essentially, what you do is you inject a sample into something called an electron gun. Okay, and what this electron gun is essentially, it ionizes every compound in that sample. And sometimes it breaks apart into littler compounds, sometimes it doesn't, okay? But either way, everything gets ionized, okay? And once everything passes through this electron gun, it enters this area called a magnet, where all the ions get separated based on their weight. And the way they're separated is how well they interact with this magnet that surrounds this tube, so to speak, okay? So a heavier ion will immediately gravitate towards this magnet, lighter ones later on. But just the right ionized particle will travel through and hit the detector, okay? Now, eventually, all the ions will hit the detector, okay? And once it hits the detector, it will go through some digital program to spit out what is called a spectrum, or a visual of all of the ions that were in that sample. And working backwards, you could figure out the identity of the identity of the compounds that were in that sample. Okay. All right. So let's say we ran a sample and it gives us a mass spectrum. Okay. Now, before I give you an actual mass spectrum or a basic one, it's important to know what is included. Okay. A mass spectrum is basically a plot between the ratio of ions and its abundance. So here on the x-axis, we have something called m/z. Okay? And on the y-axis, we have something called the relative abundance. Okay? The m/z is basically the mass divided by the charge. Okay? And in the scientific community, we usually call this the mass to charge ratio. The most common charge is +1. Okay? Depending on the source, your mass spectrum could have an mz on the x-axis, or m/e, or even just something called the mass number. Okay? But what this is that it is a plot of the mass of the ion and its relative abundance. So let's say we just did a sample of chlorine, okay? And here we have chlorine ions that showed up at 35 and 37. And if you look at the relative heights, this is a 3-to-1 ratio. This is what would be considered a fingerprint for chlorine, is this 3-to-1 ratio. And if you ever saw this, okay, this ratio in a mass spectrum, you could use this ratio to say, I think there is a chlorine present. And because this is a 3-to-1 ratio, you would see a 75% of chlorine of this isotope of chlorine and a 25% abundance of this isotope of chlorine. Okay. That information can be used, okay, to determine the average atomic mass, which is something that we've done in a previous class. Okay, you take the isotope, okay, or the mass of each isotope, multiplied by the fractional abundance. Okay, and because this is a 3-to-1 ratio, we would get 0.75 and 0.25. Okay. The product of this gives us the isotopic contribution of each isotope, and to get the average atomic mass of chlorine, you add them up. Okay, so here we have an average atomic mass of chlorine to be 35.5, which is roughly what you see on the periodic table. As I said earlier, we can use a mass spectrum, okay, and their relative abundances and the mass to charge data to identify an element. Okay, so if we were to look at this mass spectrum, take into account the relative heights and the masses of those two isotopes, what element do you think is present? That element is bromine, okay, because the only element that has an average atomic mass around 80, okay, is bromine. We can also, using the periodic table, and kind of work backwards to predict what a mass spectrum would look like. Okay, if we had two isotopes of lithium, lithium-6 and lithium-8, okay, we could get clever and predict the relative heights of these two isotopes. If we look at the periodic table, we know that the average atomic mass of lithium is 6.9. We also know the atomic masses of these two isotopes. Okay? If you remember from fractional abundance from, your previous class, this is kind of review, we can solve for the fractional abundance of each isotope and use that as the relative abundance in our mass spectrum. Okay? This would require assigning a variable to each of these isotopes, okay? And because there are only two, all right, one would be represented as the variable y, and the one represented as 1 minus y. And we just take the difference, okay? Well, if we multiply the mass by the fractional abundance, we get their contributions. So these two, the sum of these two should equal 6.9. When we take all that into what is an algebraic equation, we can solve for the value of y, which is the fractional abundance of one of the isotopes. Okay? So we distribute, okay, we isolate y, we divide accordingly, and we get a fractional abundance of 0.55. Now, if I wanted the percent abundance, I would just have to multiply by 100. Okay? But now that I know the fractional abundance of one of my isotopes, I can plug that value in to my other expression for the other isotope, and I get 0.45. Okay? These values can also represent the relative abundance or the relative heights of our peaks. Okay? So when I go back and predict the mass spectrum, I would have a peak that is slightly higher at 6 than 8. Okay, and then if you go across, that could be about 55, and this could be about 45. All right, that's it for today. Thank you for your attention.